Hello, so this is Avirup again. So we have left with the limit operations, the definition of limits, the algebras of limits. So in our last session we have discussed about the approach of limit, or the how should intuitively limit can be defined. So so our so let us quick revise that what we have defined in our past classes. So so we have defined that an intuitive approach of limit even we have defined the formal definition of limit, that is the epsilon delta approach. So the definition of limit, that is epsilon delta approach. Okay, so epsilon delta approach. So here the intuitive approach was the limit, that is the limit. So it defines that, let me use another color. So it defines that limit, if I take limit of a function, so that is x tends to a, which is L. So but in epsilon delta approach it is said that uh, the definition is, the formal definition is for all epsilon greater than 0, okay, and it doesn't matter however small it is, and there exists a delta positive, okay, which is such that this f of x minus L is evaluated less than epsilon whenever this x minus c is evaluated between 0 and delta. Okay, so and from here we have seen a graph. So it was like this. This was the graph, this was the y equals to f of x, and we have seen that something so we have seen this graph. So let me insert this graph here again. So yeah, so this was the graph. So let me insert here this graph. So you have seen this graph. So this graph says that, and it illustrates that for a given epsilon 0, that epsilon greater than 0, for a positive epsilon we can draw y equals to L plus epsilon and y equals to L minus epsilon, and the graph of this horizontal function, if the limit exists, then we find a number, a positive delta, okay, such way it is restrict the where the x lies between this x lies between this x um, lies between within this range within the open interval c minus delta comma c plus delta. Okay, and the curve that is a, so here it is the curve or the function y equal to f of x. Okay, so that was the thing. And even we have discussed one problem there, but it wasn't sufficient at all. And we also discussed the left hand and right hand limits. So so in the definition of limit, we know that limit exists if and only if the both of the um, limit exist. I mean the both side, both the one-sided limit exist. That is, the theorem was something like. Uh, so let me write it. So so we write that limit of this function which approaches to x towards c is L if the both side limit, so x approaching towards c negative, that is the c negative, yes, so that will be L minus, and L limit of x tends to c positive of this function, so that L plus. Okay, so that is the thing. And yes, so both has to be satisfied. I mean equal sign will be there definitely, so which is equals to L. Okay, which means this. So this was the things. And obviously the here was the limit algebras. So you know this limit algebras we have defined. So we have already discussed these main three definitions, and how we'll approach for a problem. I'm coming to that, but before going to the problem, we'll discuss important theorem for a problem solving perspective, that is the squeeze theorem. Okay, so what squeeze theorem says, so see, in calculus context, the squeeze theorem, or you may be heard about the sandwich theorem, both are the same thing. So this theorems is regarding the limit of a function that is trapped between two other functions. Okay, so you can see this graph maybe a great. So before going to the hardcore definition and proof, this graph may be the one more intuitive understanding which can makes you convince that uh, what I am trying to say. So that is the thing. So the squeeze theorems is used in calculus uh, to confirm the limit of a function via comparison with two other functions whose limits are known. So let me write that. So the squeeze theorem, so the squeeze theorem is theorem regarding the limit of a function that is trapped between two other functions. So this is the intuitive definition. So if someone asks you, just tell me the idea or the concept of the squeeze theorem, so this will be your answer, that the squeeze theorem is a theorem which shows us, or which say that a function that is trapped between two other functions. Okay, so you see, the squeeze theorem is basically used in calculus to confirm the limit of a function via comparison. Okay, so moreover, okay, moreover, so let me use another. So moreover, in calculus, this theorem confirms that the limit, okay, the limit of a function via comparison with two other limits, you see. So let me go to the next page. Two other functions whose limits are known. Okay, so it was first used geometrically by the mathematicians Archimedes and Eudoxus, okay, in an effort to compute pi. Okay, so now I will go to the formal definitions of squeeze theorem. So it is says that if this gx is between two functions, say hx and this f of x, okay, so when this is near a point, say a, okay, so this a is so it is claimed that except possibly at a, okay, so at a, okay, so limit of function, okay, so if we take the limit, okay, so if this h take the limit of f of x and this h of x, okay, then if it is approaching towards a limit called L, then this gx also approaching towards L. So it means that, say, this so let me use, so if this function, rather you can say the sequence of function also say, but I won't use the sequence of function because that is another definition and another mathematical approach. So you can assume that one thing, that if this is f of x, okay, is approaching towards a limit, okay, or don't say so so yeah, you can intuitively say like this. And here it is, this say um, so this is gx, okay, so there is gx, okay, so there is gx, and this sorry, not gx, so this is h of x, okay, this is h of x, and this is the gx, okay, so you can say like this, okay. So if you compare with that idea of if you heard about something called sequence of things, so intuitively you can say that if it approaches, this green line is approaches towards uh, a limit or towards a converging point, okay, and this blue lines also approaching towards a converging point, that is trying to so in a very long run or in a large number of cases, so it is approaching towards a number, towards a figure. So then so as this hx, okay, so this uh, this hx here, and you can say this f of x here, okay, so let me write, so here, so this is hx, so here it is hx, and here it is f of x, okay, and both the thing approaching towards a figure. Then if it is between, in this two functions, between two functions, if there exists a function that is gx, okay, then this function's limit also approaches to this limit. So that is what we stated, that when x is near a, okay, except possibly at a, okay, possibly at a means so it is not attaining a or exactly a, okay, it is approaching towards a, that what I want to mean, okay. So that's how the things is defined, okay. So this is the, so let me highlight this, so this is how the things is defined. So you can take these notes also, yes. So this is the thing, okay. So now we'll do some problems with the epsilon delta definition of limits, okay. Even we also do some sort of problems which is associated with the limit definitions we have discussed previously, from the algebraic definitions also. So let do the epsilon delta definition, explore the epsilon delta definitions for to problem solving cases or purpose, okay. So first prove the squeeze theorem, okay. So first prove the squeeze theorem, then we'll jump to the problem. Okay, so let me go to the next page. Okay, so proof. So we'll write the proof. So let us write the proof. So so uh, so for a so for all, so we'll start from, so for all, so we'll write the epsilon delta definitions as we prove when we prove the epsilon delta definitions by providing the arguments. We'll use that arguments, that is the for epsilon positive for all, or the for every epsilon positive there exist real, there exist are delta positive. Okay, so such that so definitely you can write a real delta positive. Okay, so such that for all x, for all x uh, with for all x with you can write for all x with this, or you can write it as so such that yeah, as you have previously defined, so you can argue that also, but I am giving the argument in a different way, so doesn't matter, but the context may not does matlab, what I am to trying to say that the in the context you are providing the argument, that shouldn't be changed. Okay, so you are providing the context, you are you are providing the argument in the context of defining the epsilon delta definition, and from that you are trying to prove the squeeze theorem. Okay, so whenever you are providing any argument to show or to prove some consequences or some theorems, so keep it mind whenever you will provide argument. Okay, so or it doesn't matter what is the process or what you are writing, providing, um, however you are providing the argument, it doesn't matter, but the context or the things, the consequence may not matlab it shouldn't be changed. Okay, okay, so please keep it mind. um, yeah, so we have this, so f of x minus L. Okay, this is the things. So more generally we can so we can argue more generally, more symbolical manner, we can provide the argument like this, that for epsilon for all epsilon positive there exists a delta positive, delta real, such that for all x, okay, with modulus x minus a is lesser than delta, which implies that this f of x, okay, this f of x minus L is evaluated with this lesser than this epsilon. So as it is written, so we can say that as limit of x tends to a, so uh, so let me see. So as hx, as limit x tends to a, so h of x is equals to a. So what we can say, or what we can write, that is uh, so it means that mm, means that uh, so for again same definitions, the same way we'll define. Okay, so okay, wait, maybe I'm doing something wrong. If it is hx equals to l, so it means that yeah, true. So for all, so as it is defined, so we can claim that for all epsilon um, 0, okay, there exists delta 1, okay, delta 1 greater than 0, such that for all x with this modulus of x minus a is defined, so this will be delta 1, which implies that this f of x minus l is lesser than epsilon. Okay, so not f of x, sorry. uh, so this is the generalizations of um, wait, so wait, so according to this, so this will be for gx, I'm sorry, so this will be for gx. Okay, so this is the in general definition. Okay, so for gx, so for gx it is defined. Okay, and this is I'm doing for hx. Okay, so I'm doing for hx. Okay, okay, so that is so this is hx. So again limit of so it is as it is given, limit of fx, okay, x tending to a equals to l. So what we can say, so we say that for all epsilon positive, okay, there exists delta 2 which is positive, and for all x, such that for all x, so same thing we'll write. So this will be changed, uh, this is for delta 2, which implies this f of x minus l is this. Now we have what we have, so we have this is 1, okay, and this is 2. So we have then we have gx lesser than not gx lesser than, it is hx lesser than gx lesser than fx. So this is sorry hx lesser than hx is f of x, and here the g of x. So we have this, so this is given to us. Okay, So let me make you understand again that so the argument I am providing for uh, this is for sorry so this is for so this is in general for gx. Okay, so this definition will be in general for gx. So first I am claiming that as hx equals to l, okay, as the limit x tends to hx equals to l, so therefore I am taking a delta 1, so delta 1 positive 0. So for that so I am saying that this, if it is satisfy these conditions, okay, so you know that how to provide the argument of like this. So if it is so, so we can write this, okay, so we can easily write this for hx. So it is easily write for hx. Now so for f of x, I mean, so for h of x, this definition, for f of x, this argument, okay. Now gx, so now we choose, so as it is provided, and you can write that hx, so I'll write, so in the next step we'll write if and only if hx minus l, that is in between yeah, less than equals to gx minus l, this is f of x minus l, okay, right. So we can choose, now we can claim that we can choose that is a delta such, the delta such way that it should be minimum, okay, minimum of delta 1 comma delta 2, okay. Then if x minus a within this given conditions, I mean this x minus a evaluated, which is lesser than delta, so we'll combine, so combining 1 and 2, what we will find, we have the x minus a lesser than sorry not this, we have this minus epsilon lesser than gx, okay, minus l, and this is not gx, it will be hx, sorry, so hx, okay, lesser than gx minus l, and this is f of x minus l, okay. And if it is so this means minus epsilon f of x minus I mean the g of x, this is g of x minus l, which is the positive epsilon. And if you do more step, so if it, this is if and only if, okay, so if you do more step, so you will see, so this g of x minus l is between this epsilon. So we have we have proved our required consequences. success. So we are proved. So I'm stopping this part here again. So in the next video will be all about the problem solving session of how the problem can be deal with the epsilon delta approach and squeeze theorem related to some sort of problems and consequences will define in our next session. And if there is any background noises and interruptions, I am deeply apologize for that, so please forgive for that, because I am recording this session from my institute, so there might be some sort of background noises and interruptions, as I don't have that much of equipments to do so. But if you receive the insights, the informations, or the quantity of knowledge, the quality of knowledge, so if you utilize that knowledge for your exam or your goals, what you want to achieve, so then my teaching, my the things which I am sharing with you, the lecture which I am deliver, it will be fruitful for you and me as well. So thank you for your patience, guys. So I am ending here.